Okay, so in terms of thinking about buildings and really trying to approach them more as a series of systems, I'm really going to get back to almost really what we did. I'm going to do it online, so it'll be a little bit easier for other people to follow too, who are out watching it online instead. Okay, so the idea is we have these buildings, and what we want to start doing is thinking about them as a series of systems as opposed to thinking of them as just sort of completed wholes, because they are made up of all of these separate parts that are all finely tuned and work together, and hopefully all work together in a very finely tuned way that is compatible with the environment and uses the least amount of energy and things like that. But it's important to note that really everything is kind of designed against specific types of criteria that are really driving each of the different systems. And as we design each of the different systems and optimize them for the criteria they need to be designed for, but every once in a while, things come in tension or work in opposite directions, and we have to make sort of trade-offs as we do the overall design, but that's just part of our role as the designer to think about that. So really, if we think about the different types of systems that tend to be involved in the building, an analogy that you'll hear used, especially if you're in the PBL class, but it sort of applies in a lot of different ways, is thinking about buildings almost like the way we think about our human body. We have all the different systems that are involved here and knowing what the parallels are in a building to go ahead and make it work. Because we have our finished final form here, but we're really this incredibly finely tuned series of systems that all need to work together. And let's think if we can actually kind of draw analogies between those different things. So in terms of the human body, like what are some of the different systems that are part of the human body? We'll think about really what the building equivalents there are. Okay. So like, what are some of the major systems of the human body, if you're going to think about it from a systems perspective? Yes?
Respiratory.
Excellent. Okay, so that's all about moving air in. It has a couple different purposes. We have to kind of bring in air to keep us healthy and kind of supply all the different pieces that need the oxygen and stuff like that. We also have to sort of exhale that air, kind of relieve, exhaust all that type stuff. So really, in a lot of ways, that's very similar to our ventilation systems. Okay, what are some of the other big pieces of the human body? Got a lot of them. Yes?
The circulatory system.
Yep. Okay, so for the circulatory system, what's that doing for our human body? What's happening through it?
It's like cycles the blood of the system. It's like kind of what gives the body life.
Okay, so it's bringing blood. It's part of it's bringing these fluids, stuff like that. Okay, in a lot of ways, that's actually very similar to our, I'll call like our water supply systems. Yeah, we also have our like water waste or drainage systems. Yeah, but it's all about this whole thing that like our it's kind of interesting. Yeah, like relative to that, the heart's kind of a really interesting thing relative. Yeah, in terms of thinking about it. Yeah, what's the equivalent of the heart of the building? Is there one?
Well, I guess the heart's kind of like I don't know. I guess the heart powers the majority of the house.
Yeah.
The person.
Yeah.
The heart. Yeah, I just powers the person. So
It's yeah. It's funny. I'd say it's the mechanical room, wherever that is. It might be in the basement. It might be down. Yeah, it might be up in the attic. It might be a number of different places. But I think the mechanical rooms are sort of like that. It's really where all that heavy-duty equipment, which is going to pump fluids or pump air or do whatever it is for the whole system. It's kind of interesting. It's sort of very similar to that. It's interesting on the respiratory front over here. Yeah. Our lungs is what we sort of think about relative to that type stuff. If we kind of think about the equivalent kind of in our context, it's really more like it's air handlers. The air handlers that are out on the roof or down in the basement. And then somewhere, part of the circulatory system is also like all the duct work. It's a question of whether we have duct work as part of the respiratory system, the circulatory system. It's more like piping. Beautiful. What are some of the other big systems in the body? Like that. Yeah, the skeletal system's huge. Okay, and what's that most equivalent to in a building? Yeah. Okay, and as we think about these things, there's really, it's funny, there's almost subsystems within there that we, don't think about so much. There's the whole notion of, the part that actually just kind of keeps us like vertical and erect and stuff like that. There's the whole notion of like the gravity systems. But there's that whole other thing of like the lateral stability and really what keeps us from like kind of tipping over and stuff like that. And that's, again, there's this very direct parallel. Got it. Okay. What are some of the other big systems? Like, yeah.
The nervous system?
Yeah, the nervous actually. Let's think about that one. Okay. So we got all these like little impulses and sensors and things that kind of connect it all together. So I got all these sensors. It's funny, like sort of the wiring that kind of ties it all together. And then network, so some of that wiring's power related, some of that's sort of network and signal related. There's a lot of different pieces to that, but that's almost kind of like the smarts. It's interesting. Do buildings have a brain? Yeah, it's funny, they didn't used to necessarily have a brain. Nowadays, actually, we've sort of learned that having a brain is a useful thing for a building. So the whole notion of a building management system, okay, the control room, that's becoming increasingly common as something, because as our buildings get more and more sophisticated, you really need some central coordination, some intelligence to actually sort of pull it all together. Cool. How about like this stuff? Like just the skin on the outside. I guess it's an organ. I think of it as sort of a system. Let's think about the skin and really what it does for us. Because the skin does a lot of different things. It goes ahead and it protects us, kind of holds us in. So it's kind of containment. Okay, what else is the skin good for? Probably keeping us in there. How does the skin work with some of these other systems? How does the skin sort of work with like the circulatory system or something like that? Skin's actually a pretty amazingly smart thing in terms of like why we sweat or like how we cool ourselves and stuff like that. There's really a lot of just kind of,
It lets the body breathe, so is it kind of related to like airflow or something?
yeah. Because there's sort of this breathing thing, and that breathing thing it's good for a number of different things. It's good for this whole notion of kind of the intake, okay, but it's also good for, there's kind of this whole cooling effect that goes on there too. It's really a bunch of those things. Okay, and really the whole skin and how we approach the whole issue with the skin and the things around that, it's very much like the building envelope, really, and put that in there. Okay. So, we really, in some ways, we want to start thinking about our buildings as actually having kind of very similar properties to the human body. The body is actually a pretty finely tuned organism. It does a pretty good job of being a self-contained, like living, breathing, kind of energy. It does an awful lot of things in a very, very good way. And it's actually good to start thinking about our buildings as having similar sort of, kind of properties, and ultimately thinking about designing them so they work in similar ways. Because one of the very enlightened ways of thinking about buildings is, as opposed to thinking about them as being these static things, which is produce them once and you put them on the landscape and they are there as these static objects, to really thinking about them as organisms that can dynamically change and interact kind of symbiotically with the environment, so that as people and loads and needs and the environment is changing, the building can be changing in response to that, kind of like our human body is. Yeah, so it's a kind of a good way and a good guiding principle for that. Actually, for all these systems, yeah, is there a hierarchy to them? I'm not sure if there's a hierarchy. Or there's definitely sort of an order to them. Yeah, it kind of gets to almost how we design buildings a little bit. Like, of all these different systems, like, you know, like, at least if you were building a human body, where would you start? What would be the first system that would come? Yeah. So it tends to start with that, which is actually kind of amazingly appropriate because, you know, sort of the same thing happens with our structures. We tend to build the structure first and really use as a skeleton or a framework to really hang a lot of the other systems around that. Okay. Then within that skeleton, we tend to do things like going through and just putting all these functions, you know, things like the air handling, the circulatory system, the nervous system, that all sort of hangs off of the skeleton in terms of what's going on. And then finally you have kind of this skin sort of wrapping it up. So, let's see. I'll just put I'll put my heart and my nervous system. Well, actually, I'm going to put the nervous system out here for a second. My lungs. Okay. Skin. What is that? That's kind of, let's put it out here in closure or something like that. It's sort of, I guess I'll call it the wrapper. Okay. And then finally, these last two ones here about having a nervous system and ultimately having a brain, really that's all about this whole notion of controlling. Because, kind of in the same sense, if we didn't have those, we'd kind of be in trouble too. But that's not a bad hierarchy for thinking about really, you know, how we approach designing buildings, starting with the skeleton and working on all the infilling systems that are, they're supplying all of the essential fluids and air and everything we need to actually be a good living, breathing organism. We need to wrap it all up, and finally we need a control system for making it all work together. And yeah, in some ways that's a pretty good analogy to what we're going to be doing with buildings too. It's actually in some ways the order in which we're going to be approaching it in the course too. So starting with the skeleton, then building up these infilling systems, and kind of getting more, well, I'm going to switch it up a little bit. I'm going to put the wrapper stuff first. Then we'll get to the control system at the end. Okay, beauty. It's really just wanting you to start thinking about each of these things as a separate system, and then for each of these different systems, to almost think about really, it's this whole notion of really what are the driving criteria. So let's see if we can sort of articulate those a little bit in terms of really what's going on. Yeah, when we think about gravity systems, really, you know, what are some of the external interfaces, or really, what sort of drives our gravity design? Yeah, how do we design like our structural systems? Really, what sort of criteria ultimately sort of dictate why they are what they are? So, like, if we're thinking about the gravity systems, what sort of things determine like how long our beams can be, or you know, what size they need to be? You're waving your hand. You almost wave, so I'm going to call on you.
I think the stress or the information.
Sure. Yeah, there's a couple of different things. Just this whole notion of loads and stress. I'm going to learn a lot of that ultimately gets dictated by, there's different sort of locational properties that dictate a lot about what our loads are going to be. There's different loading criteria that come from building codes and stuff like that. So, yeah, they come from like building codes. Okay. And we have all the material properties. They kind of like dictate all that type of stuff too. Really, at the end of the day, really, what's our goal? You know, how do we know if our gravity system has succeeded? You know, why is my gravity system design better than your gravity system design? what's essential? What's the bare minimum it has to do? So, what would we say about your beam system that if this happens, it's a success. If it doesn't happen, it's a failure. So, what does it got to do at its bare minimum? Yeah, pretty much not fail. It's pretty simple that way. As long as it basically like carries the loads, not fail, okay, and preserve people's life safety and things like that, you'd say that's kind of sufficient in terms of what's going on. Okay, but if we decided to go one step further in terms of thinking about a system, okay, if I have two different systems that are both going to carry the load and not fail, what might be some higher level criteria we could use for deciding that, my system is better than your system, yours is better than mine? What other things can we look at to help us decide really what the better system is? So what sort of things can we consider? What's that? Yeah. Economic is always a good consideration. So by that, we can think about just, the cost, how much this system costs versus that system cost, and try to hopefully choose one that is a little less costly. How about, do we ever think about things in terms of, what I'll call it, the embodied energy or something like that? Yeah, it's another way of looking at it. Of all the different materials we're choosing, can we go through and actually design something based on the notion of the materials and really, go for one that actually has less embodied energy kind of consumed in the structure, something like that. Then, ultimately lowering the carbon footprint of what it is for building that building. There's kind of a really interesting building in Shanghai, the Shanghai Tower, which actually has kind of a cool story along these ways, where it's arguably the most sustainable building in the world right now, where they, in designing it, did a couple different things. Through just the design of their system, they went through and designed a tower that, what does it have? It kind of has a shape that looks like this. Okay? And it's not only that shape, but it kind of starts at the bottom and rotates and twists and tapers as it goes all the way up the building. And it's kind of a really cool design, because what they ended up doing in designing this was kind of took into effect one of the biggest considerations when you're designing a tall building is wind. And the nice thing about designing this shape is that, and with the taper, in almost any orientation, wind's going to flow around it, as opposed to actually, if we had a building that looked like this, it would be hitting that face and introducing an awful lot of stress and putting an awful lot of load on that building. So it's kind of a really cool design, because it went through and tried to design a shape that was really a little more sympathetic towards the wind. Okay, by doing that, they're actually able to save, it's kind of interesting, 25% of the steel, which is actually pretty huge. That was like a $50 million savings or something like that, which is pretty good in terms of building the building. Yeah. The other thing, though, that I like to think about relative to it, though, is that by saving that 25% of the steel, if you just think about that from a sustainability standpoint, that's a whole lot of steel that didn't get consumed in that building, which is actually pretty good. So, so a lot of ways you can think about criteria to drive things. And what we're going to be doing in each of these different systems is really starting to think about what is the driving criteria? What is it that just sort of is sufficient, give you bare minimum, but really what is it that makes it better? Because for each of those different things, you could say there's some things that make them better. So, when we come to ventilation systems, we have to provide a certain amount of air just to go through and maintain an air quality within the space that's dictated by code. There's a whole another issue of whether the space is fresh. If it's actually kind of comfortable or it feels sort of stale. Actually, this room suffers from that a lot of times because there's so much heat off of the computer. But have you ever walked into a room where it feels like a locker? It feels like a locker room. It just has that sort of heavy, moist, kind of stagnant air feel. Or, I'll admit to this, have you ever gone over to Grandma's house and it just it smells like Grandma's house? And it's just, it's just that kind of musty, kind of stale air. Because grandma just doesn't open the doors and windows as much as she ought to. There's that sort of thing going on. So each of these different systems, there's things that are sufficient. We can certainly design a water supply system or a water waste system that takes care of just bringing the water into a building and taking care of draining it adequately. We can think about how we can use like gray water systems or water catchment systems or something to actually go one step better and reduce the amount of fuel or reduce the amount of water that we're using in the building. You know, for all these different things, we can kind of just always think about a bare minimum and how to go further. And that's just something I want to plant in your minds, because for each of these different systems, we're going to do that. We're going to say, okay, what is the criteria, sufficient, and really what's going that extra mile? Because really, as designers, you have that ability. You can go ahead and push it the extra mile, and we could think about really what it is that's going to be most impactful. Okay, let me go ahead and I'm going to switch over to just a little bit of software. Then we'll get you out of here. Just to give you a sense of where this is all going. Okay, I'm going to go ahead and open up a product that we will be using next time called Vasari, just to give you a sense of what it's like. Just give you just kind of a notion of really this whole notion of, I want to start thinking about buildings as we design them in terms of something we'll call performance-based design. And the idea of performance-based design is it's not we're strictly looking at just aesthetics, but we're actually looking at the performance of the building. We're actually trying to understand, its cost, what the energy impact is. Just really, for every design decision, there's typically a performance aspect. Okay, just give you a sense of how this works. This is a tool. This is like a basic little building model of New York City. Okay, and the idea behind this example is ultimately that we want to design something for this space. There's actually a site which is kind of downtown, and within that we can take a look at some different potential towers that we could put on that site instead. So we have one tower that they call the Sail, which looks something like this. Let me open up another one. Something called the Layered Tower. Let me orbit around that one. This is kind of like everyone's old vision of what New York used to look like. That's a trapezoidal tower. You can't hardly see that. That, if I looked at it from the top, is more like a trapezoid. Angled, kind of like two angled elements passing up past each other. Faceted, all the way up to heavily faceted. That actually looks like some towers you see built today. And finally, progressive facet. Okay, so given all those different towers, if all of those towers ultimately deliver the same amount of square footage, the same amount of usable space and stuff like that, the question is, how do you decide which is really the better design? And that's really what we're going to try and explore a little bit in this course. And let me talk about how we do that, just to kind of set a context for it. The idea is, as we're going through and thinking about these towers, or thinking about just sort of any design, it turns out everything's amazingly dependent on context. And that's where we're going to start off next time, is really thinking about context. Because it's the answer we would get for a tower and really what would make the most sense for New York City would be different than what would make sense for San Francisco or Abu Dhabi or Shanghai or Singapore. All these different locations will have slightly different answers to what actually makes the most sense. And it's really based on the local climate conditions, the wind conditions, the sun conditions. All those things factor into really what's going to be the best design for that local context. So what we're going to learn to do is, for each of our different design options, always go through and put it in a specific context. A specific context that'll let us do things like, let me kind of turn on the shadows here for a second. Kind of cast accurate shadows in terms of what's happening with our building, or look at the whole notion of, kind of pull on out here. What's happening with those shadows at different times of the day and at different times of the year. So for example, in June we have a certain set of conditions. If I go ahead and move myself over to like December, we have sort of a different set of shadows that are being cast. But you'll find out that's actually very, very sensitive to the location where we are. Like right now, we're in New York City, so in New York City you're starting to see these long shadows that are cast because we're far enough north. We have a high enough north latitude. If I went through and switch that, let me try that. Okay, log myself in here. Okay, give me a location that's much closer to the equator. What's a good city that's near the equator? What? Quito? Okay, let's try it. What's the latitude in Quito? Well, it's in Ecuador, so I'm assuming it's very close to the equator then. Okay, very good. Okay, you notice there's different weather stations relative to, what's that? Is that the proper name of Quito? Or is that
No,
like,
that's
that's a different city.
No, that's a count.
Was that? That's okay?
Canton means count. That's fine.
That'll work? Okay. There's different weather stations. There's data sort of about weather all over the world. What's going to be important. There's a latitude and a longitude associated with this. Let me go ahead and pull that in there. Okay. And now, this is interesting. Okay, I'm early in the morning. Let me go ahead and pop up to just later in the afternoon. That's way in the morning. I went the wrong way. 5 a.m. Oh, don't do that. No! Okay, forget that example. As usual, software will crash on me. The point is that really, as you're going through and thinking about like sun and shadows, like the whole notion of location really is important. Let me kind of show you the other thing that we start thinking of, some of the other things we start thinking about relative to performance-based design. For example, here we're looking at New York again. There's this whole notion within the city of really what is the effect of, in a complex urban space like this, the effect of solar radiation from all of these buildings, how do they all work together? And there's actually good tools available that let us do that. If we have a context for placing our buildings, we can start to analyze and understand really the amount of sun that's hitting an individual surface. Let me show you how that works. So there's a whole suite of analysis tools that are available to us. They're all about informing our design. One thing is this whole notion of just the amount of solar radiation on any surface. And that can be really useful for either understanding how much solar radiation is hitting our surface, then we know a little about how much either potential we have for doing photovoltaic generation on our own surface, or we could go ahead and think about how we're shading other buildings, which is also a very big impact in terms of a lot of the planning that we do these days. So I'll just go through and kind of select a relatively simple one. I could really do it for almost any surface in the model here. But the idea is that we could go through and just choose some surfaces. Let me grab that surface and this surface, and I'll grab that one over there, and some of these ones that are down in the tunnel a little bit, or down in the canyons. Okay. And the idea is, what we'd like to do is actually understand a little about the solar radiation and very quickly get some feedback. So what this kind of feedback is actually showing us is, this is actually the amount of solar radiation that's hitting cumulatively. I can look at a peak radiation, I can look at it across a single day or across an entire season. But you start to see that the effect of the buildings on each other is actually pretty dramatic. What's going on, for example, in this building here, down here in the lower portions of the building where you're seeing all that blue and purple, what's going on is the shading from the buildings around. Just as the sun moves through the sky throughout the day, the shade that's cast by this building, later on in the day by this building, is actually keeping the lower portions of that building shaded. They never hardly get any solar radiation down there. Whereas up here at the top of the building, you're getting a fair amount of it. Over on this one, it's much easier to see what's going on the river here. On the east side, seeing a lot of sun in the morning. But through the day, you see that there's really very little of the building that's getting much sun at all. Right? And that's the kind of thing we want to start thinking about. It's really just, for any different building design that we propose, really what is the impact of the solar radiation? One of the other things we're going to start looking at, though, is something like this. we'll start looking at okay, this is that same context. This is actually a wind tunnel. Okay, let me go ahead and just pull that down a little bit so you can sort of see. The idea is as you go working through, in this case, the wind is coming, looks like it's coming from sort of the southwest over here. You're starting to see that there are different high velocity zones, there are different lower velocity zones. In certain areas, like right in here, we have like a real little wind tunnel. Also coming up this way, we have a little wind tunnel going on there. There's some spots that are a little bit deader. And we can be thinking about this kind of at the city level. We could be thinking about it at the building level. So as you're thinking about a building and trying to figure out, is that rooftop garden actually going to be bearable? Is anyone ever going to be able to sit up there? Or what times of the year can they sit up there? You can actually start analyzing and determining these things. Go ahead and I'll pop this around. If we want to go through and, for example, change the wind to, come on you, there you go, a different direction. We can go ahead and do something like that and really understand what it's going to be like. And this is not really arbitrary. It's actually kind of very deterministic about how this is. Let me show you how this works. For a specific city, there's actually something called a wind rose, which will actually show us at different times of the year, in this case it's looking at the entire year, really what is the predominant direction of the wind and what is the intensity of that wind. What you're seeing over here in New York City, well, it looks like the predominant direction is kind of from the northwest here. The strongest, and it happens, that's probably the most predominant direction for the wind. So if we're looking at it year-round, okay, that's the effect. What's going to change that around a little bit? If I'm looking at it in the wintertime, okay, you'll see that it's actually coming from the west-northwest. If I'm looking at it for the summertime, though, you'll see it actually changes quite a bit. It's coming from the south. If we look at autumn, again, it's coming from straight in the north. And even there, we could start looking at it at different times of the day. So this is like from midnight till midnight. If we want to say really what the daytime effect is, let me just look at where the wind direction is from, say, 8 to 5. Okay, it changes a little bit. It's still predominantly coming from that direction. But you'll find that everywhere in the world, again, has very local wind conditions. And the idea is really in performance-based design, we just want to think about these things and then really adapt our buildings so on that windy side, we have some wind protection. On the other side, we don't have some wind protection. But really trying to optimize the building for the local conditions. Okay, so that's the beginning of performance-based design. Where we're going to go after we just kind of start thinking about things from a performance-based standpoint, though, is really starting to think about these buildings as a series of different integrated systems. And let me just give you an example of one that's put together, so you can sort of see where we're going to be going with this. And then we'll wrap up for tonight. I'm going to open up this tool, Navisworks Managed. I think a lot of you have played around with, especially here in the construction management program. I'm going to open up a series of models that were created of something called the Audubon Center. Okay, and this is kind of a nice little building that has a lot of the different systems articulated in them. So as we go through and do our design, in 110 or in 120A, we were sort of very much interested in the architectural features, the doors, the windows, the ceilings, things like that. You see, this building actually has some other things kind of going for it. It has, if you look above here a little bit, it has lighting, it has ductwork, it has structural systems, it has all these things. And what we're really going to learn to do is actually start stripping away a lot of these layers. So for example, let me hide the architectural layer so that we can really start thinking about this building in terms of the structural systems, the lighting systems, the mechanical systems, and how they all work together. So we may never have really thought about it much in terms of how a bathroom is arranged, okay, in terms of both the water supply and the water waste. Looks like we have some pumps over here back in this room. but even to think about all the ducting systems, both the supply ducts and the return ducts and how they're all working together. It's really trying to understand buildings at that much higher level where, you know, behind those walls, above this roof, like there really is an incredible complex network of things that are all working together to go ahead and deliver the air, deliver the water, and deliver all the systems to where they need to be. But really is typically hidden, and most people never really get much of an understanding of it. But that's what we're going to be doing together, is really learning to understand all those things, and then for each of those different things, being able to say that, you know, this specific pump has a set of characteristics. Looks like it's some 100 gallon per minute pump, but it's doing things that has a very specific requirement. We're going to learn not only how to go through and size things like this, but actually how we actually size all these systems and understand as they go routing through the building and have all the bends and twists and turns, not only how to avoid conflict with other things, but to understand really what the efficiencies are. Because for each of these different systems, for every bend, for every turn where we lose a little energy, we introduce a little bit of friction to the system, you know, you're ultimately making the system work a little bit harder. So that the pumps get, they have to be sized up a little bit. So all those things have sort of a huge impact on what's going on. So really, that's where we're going with the course, is really learning to look at buildings in terms of all these, you know, underlying systems. Yeah, and at the same time, hopefully still be able to appreciate the architectural systems that are kind of happening at that high level. Let me pop back in here. There we go. Looks like I'm in the heart of the building. Pop back out here. Nope, through the restroom. Trying to get back to any place that looks reasonable. Yeah, we'll get on out. I'm floating in air upside down. That's not very good. Oh, there's the foundations. I saw all the piles right down there. Okay. But then up underneath it. Go ahead and take a look and understand the building. Okay. So let us go ahead and break there for tonight. Okay, I have a pretty good sense of where we're going, all this stuff. So where we're going to go next time is specifically looking at all those contextual things. We'll be looking at the whole issue of location, and how the weather, and the latitude and longitude of the sun, how all that factors in, and how we can start using the SARI to kind of make some very quick decisions about the overall shape and form of the building. And then we take that and then start articulating an envelope relative to those so that the different sides of the building actually reflect the local conditions and what's living on this. And then we'll move into more this kind of systems design and all the circulatory systems that work around inside the building. Okay, so let us break there for tonight. Again, next time, please come back at 5:15, and we will keep the whole story going. Okay, if you have any questions, stick around, and we'll try to answer them.